Welcome to Study Loop.
Basically that distance, right? It's the diameter of the wire actually in these coils, not the diameter of the full loop itself. That is then connected to a 600 ohm resistor. And what we want to do is graph the current as a function of time through this kind of apparatus. So why would there be a current at all? Well, there'd be a current at all because of Faraday's law. So there's a flux, there's a magnetic flux through this coil because of this magnetic field, and it's changing in time. And we know that whenever there's a changing magnetic flux, there's an induced current. So Faraday's law is going to be a good place to start. So we have that the EMF as a function of time is the number of turns times the rate of change of magnetic flux. What about the current? Well, the current is going to come from Ohm's law, right? So Ohm's law tells you that voltage is equal to current times resistance, right? So therefore, current is just voltage divided by resistance, or the current is the EMF divided by R. So the current is N over R times the rate of change of magnetic flux. Okay, so that's sort of our starting point formula. So what is R? R is the total resistance of the apparatus. So it's going to be our 600 ohms plus, let me rewrite this. So it's our 600 ohms plus the resistance of the copper, right? So that's the resistance created by all of this wire, looped around. All of that wire has its own resistance. So what is that? Well, to calculate that resistance, we can use the fact that we know the resistivity, right? So the resistance of copper is given by the formula for resistance of a cylinder. So that's the resistivity times the length of the wire divided by the cross-sectional area. So the resistivity we know, so let's just leave that as rho. But what about the length? So the length is how much total wire is wrapped around this coil. So for each turn, there is a length of wire equal to the circumference of that circle. But the circumference of that circle is 2 pi r, right? That's the formula for the circumference of a circle, and the radius is r. But how many turns are there? Well, there's 500. So there's n equals 500 turns. That's n, right? That's usually what we call n is the number of turns. So that's the length, right? The length of a turn divided by the number of turns. Then the cross-sectional area is pi times r squared, but we're given the diameter, so I'm just going to divide that by 2, right? We're given the diameter up there. And we can make a bit of a simplification to 8 rho Rn over d squared. And now you can just calculate this, right? So we know the resistivity, we know the radius, we know the number of turns, and we know the diameter. So you should find that this is 3058 ohms. And therefore, the total resistance is 3658 ohms just by going back to that equation. Okay, so now we have the total resistance. So our formula is N over R times the rate of change of magnetic flux. Now, what is the magnetic flux? Well, it's area times magnetic field, but we have to be a bit careful. So this is N over R times pi r squared. But we have to take into account this angle. right? The axis of the coil is not aligned with the magnetic field, and therefore there's a factor of cos theta to take into account the vertical component. So it's not pi r squared, it's pi r squared cos theta, and then we're left with the rate of change of the magnetic field, right? So just to recap, I used the fact that the flux was equal to area times the magnetic field, and then the area is pi r squared with the cos theta to take into account the angle, and the magnetic field is over here. Remember, that's a function of time, so it stays in the derivative. So now you have to worry about the derivative. So B was, it's 0 times 0.120 Tesla times 1 minus cos pi t, and 0 or t less than 0, t between 0 and 1, and t greater than 1. So, of course, the derivative of 0 is just 0. So the only part that we have to worry about is this. So the derivative of 0.120t times 1 minus cos pi t, well, first of all, the derivative of 1 is 0, right? So that goes away. Then when you take the derivative of cosine, you bring out a pi from the chain rule, and then the derivative of cos, the derivative of just cos is minus sine, right? So these minus signs right here are going to cancel. So the full derivative is actually 0.120 Tesla times pi times sine pi t. So that's the derivative of the complicated part. Therefore, we can write down the final expression for the current. So the current is going to be, so it's 0 when t is not between 0 and 1, and when it is, it's n over r times pi r squared cos theta, right? So that's that factor. And then from the derivative, we get this factor. So then that is multiplied by 0.120 Tesla pi sine pi t. And that's for t less than 0, t between 0 and 1, and t greater than 1. Okay, so now this is at the point where you can calculate all of this is just a number, right? So we know the number of turns, that's 500. We know the resistance, that was the 3,600 ohms we just calculated. We know the radius, that's 4 centimeters. We know theta, that's 30 degrees. And of course, pi is just pi. So you can calculate all of this massive constant, and you should find that it's equal to 0.224 milliamps. Okay. So let me rewrite this just one more time. So what we're trying to graph is this function. So it's a function that's 0 when t is less than 0. It's 0.224 milliamps times the sine of pi t when t is between 0 and 1, and it's 0 when t is greater than 1. So that's the function that we're trying to graph. So let's do that. So let's graph it as a function of time. There's t equals 0 in seconds. There's 0 seconds, there's 1 second, there's 2 seconds. And on the y-axis, let's have the current in milliamps. So what does sine look like? Well, sine looks like a bump, right? It starts at 0 when it goes up. When t is 1, you have the sine of pi, right? But the sine of pi is 0. So actually, this function looks like this. It starts at 0, it goes up, and then when it gets to 1, it goes back down to 0, and then it stays 0. And then to the left of t equals 0, it's also 0. We should note, by the way, that the bump is exactly at 0 point, and that's the full solution to the problem 4, because that's the amplitude of that sine function. So at long last, there's our final graph. So we also have to determine the direction of the flow of the current. So to do that, let's go back here to the diagram. So if you look at the magnetic field, so is that increasing or decreasing? Well, if you draw a graph of 1 minus cos pi t, it starts at 0 and it actually goes up. Okay, so the magnetic field is pointing up and it's increasing. So in other words, the effective flux through this thing is this way and increasing. So if the flux is going out like this and increasing, the induced magnetic field will try and cancel that, and it'll go into the page like this, like that, or rather back down the page. And then if you use the right-hand rule, so point your thumb down to the left like this, your fingers should curl like this. So actually, the current is clockwise. And that's the full solution to the problem.